So this is chapter 78 for fuel systems, and so I want to start off by just kind of walking through some of the generations of the fuel systems that we have had in automotive vehicles. And so we started out with carburetors like this that were a completely mechanical way of metering fuel. And so a carburetor was a way that fuel was distributed into the motor, and it was supplied by a mechanical fuel pump that was typically cam operated. And then from there, most of the cars still maintained a mechanical fuel pump, but then we got to computerized carburetors, which are referred to as a feedback carburetor. And so these quite literally are the same 4-barrel Rochester carburetor, but this one is computerized and this one is not. And so this computerized carburetor, we included a computer and sensors and that like throttle position sensor and a map sensor and a mixture control solenoid into that carburetor. And then they got a little bit more complicated because you had all of the complexity, mechanical complexity of a carburetor plus laying in over the top of that computer controls. And these came in about the 80s and they continued on into the 90s. Then, in a need to try to manage fuel better, and as emissions and fuel economy standards increases, the carburetor could no longer cut it anymore, whether it was feedback or straight mechanical. And then we got into what's called throttle body injection, where they would have a injector, and the footprint of this was very similar to a carburetor. They basically unbolted the carburetor and would bolt down this TBI in its place. And so a lot of times that came with an electronic fuel pump, and so we upgraded kind of there. Then fuel injection came into being. There's a few different varieties of fuel injection that they look very similar. There's a multi-port style that was kind of a glorified throttle body, had the advantage of distributing fuel to individual cylinders, so a lot better at fuel distribution, but the way that it was controlled was less precise with a multi-port system. And so multi-port just fired all of those injectors basically at once. Well, then they got a little more sophisticated as computer controls advanced, and they started firing the injectors and distributing fuel according to the firing order. And so we got sequential fuel injection, where they would then start firing the injector on that cylinder's intake stroke. But the construction and components of a multi-port system versus sequential fuel injection, they basically look identical. And then those also had electric fuel pumps that were typically located in the tank and would push fuel forward up to supply it to our metering system with our fuel injectors. Then the kind of intermediate became a fuel system that would be returnless, where they would have a fuel supply up to a fuel rail of our fuel injectors and no return line back to the tank. And so whatever fuel the fuel system produced, the injectors would spray that into the motor. And so they kind of, I guess, would produce the amount of fuel necessary on a continual basis. So whatever was produced is what was used, and that was always matched, and they would refer to that as a returnless system. Then from port fuel injection came direct injection. And so you can see this is a port fuel injection injector, and this is a direct injection injector. And so a port fuel injection would spray fuel in the injection or in the intake port, where a direct injector was located in the combustion chamber and sprayed fuel directly into the combustion chamber. And with each of these changes came pros and cons. This direct injection achieves better fuel economy, but it has its own drawbacks with deposits and cost of the technology and so forth. But direct injection is kind of where we're at now, is we're using kind of sequential injection. Some manufacturers are there, and most everybody is starting to shift over to a direct injection style of system, which is similar to the way that the diesels run. And so we've come full circle with direct injection as well, because with direct injection, you'll see that as fuel injection came along, we kind of got rid of our electric fuel pumps or our mechanical fuel pumps in favor of electric fuel pumps. But then by the time direct injection came along, then they came back to a mechanical fuel pump all over again. And so this is the mechanical fuel pump that would supply high pressure to a direct injector. And so fuel pressure along the way increased steadily. That the fuel pressure from these mechanical pumps 3 to 5, then we get to TBIs, and most of them were like 9 to 15. Then you get to your port fuel injection, and we were seeing pressures anywhere from about 30 psi up to 100. And then when you get to direct injection, we're seeing a lot higher fuel pressures in the range of like up to about 3,000 psi. But none of that is really as high a fuel pressure as you would see from the diesels. Diesels have pressures that'll be up to about 30,000 psi. And so when direct injection came out on gas, they're like, holy crap, at 3,000 psi, we're all gonna die, right? I'm like, have you been working on diesels? Because they're like max pressure 30,000 psi. So there's obviously caution with those higher fuel pressures, and more caution than what we had to have over the history of fuel systems. But that's kind of the technology that came along. And so with all of this technology changes came a better management of the fuel that we were distributing to the engine. It became more efficient. Better fuel economy came along with it, and that was kind of the driving force behind it. Emissions have been pretty good for a while on cars, and that's mainly due to the sophistication of the computer control systems and some of the technologies that came along with it. But I wouldn't say that there was major gains in going to direct injection in emission standards versus port injection. In some ways, it's always a pros and cons. In some ways, it was better in terms of fuel economy, but then some of the other emissions that went up with direct injection are kind of a negative over port injection. So there's always pros and cons to that, but it's considered a net gain in technology in the fact that they're getting better fuel economy. Typically, I would say it's not a huge gain, but probably depending on the manufacturer and other things they have going on, it's probably a 5 to 10% increase in fuel economy, but every little bit helps, right? And that's how we see some of the fuel economies that we're getting now, the 40 miles per gallon and stuff like that out of these cars. So we'll go ahead and jump into our PowerPoints here now. So the purpose and function of our fuel system here is we want a fuel system that has the ability to store, transfer, and mix fuel with air. And so we don't want to just, it's not a random thing. This is actually chemistry now at this point, that we're always trying to meter the correct amount of fuel for the amount of air that came in. And so this is referred to as a stoichiometric air-fuel ratio, or the chemically correct air-fuel ratio. And so for gasoline, that proper air-fuel ratio is 14.7 to 1. And so that is by weight. That is 14.7 parts air to 1 part fuel by weight, all right? And so that could be 14.7 pounds air to 1 pound of fuel. That could be 14.7 grams to 1 gram of fuel. But that's that ratio that we're trying to achieve. And the idea really is this, is that all the fuel that we use is a hydrocarbon fuel. So it has a hydrogen molecule and a carbon molecule. When you mix that with the proper amount of air and burn it, then the oxygen that's in the air combines with the hydrogen and makes H2O or water. The carbon combines with the oxygen in the air and makes CO2 or carbon dioxide, which both are considered harmless, right? Except for CO2 nowadays. So depending on who you talk to, now CO2 is a freaking greenhouse gas, right? It's killing us all, allegedly. So the air-fuel mixture that we're after is the proper chemically correct air-fuel ratio for gasoline. We refer to that as stoichiometric, 14.7 to 1 by weight. In another term for stoichiometric that they tend to use in European countries is lambda. And so your German manufacturers will use lambda instead of stoichiometric. But a lambda of 1.0, all right, is a equivalent to stoichiometric by ratio there. And so whatever comes out the tailpipe of a car, we can actually reverse engineer the gases that are coming out of the tailpipe and determine the air-fuel ratio that it's running at. And so this web link that's here will take you to what's called a lambda calculator. And so you can plug in numbers for hydrocarbons and CO and NOx and CO2 and oxygen, and you can determine the chemistry from what's coming out the tailpipe and determine the air-fuel mixture that a vehicle ran at. And so we typically use that in the smog program to determine if the vehicle's in proper control of the air-fuel mixture before we put expensive components on it like catalytic converters, which is why you kind of see that reference there. And so if a car is overfueling, we refer to that as running rich. And if a car is underfueled, then we refer to that as running lean. if we don't add enough fuel, then you can have misfires. If you add too much fuel, you can have misfires. And so there's even a balance for what you can run an engine on, which we'll look at some of these air-fuel mixtures. So the air-fuel mixture is rich and lean as far as that goes. This tends to be about the max and rich that we can run an 8-to-1. And so the performance or horsepower air-fuel ratio for gasoline is about 12-to-1. And then the max lean air-fuel ratio that an engine will run on is about 20-to-1. And so that's a gross over amount of air to the amount of fuel. 8-to-1 is not enough air to the amount of fuel, and so you run too rich in that case. And so the early fuel systems were purely mechanical. They were carbureted. And so the carburetors work off of a mechanical principle with a Venturi effect. And so what they do is, and it makes a ton of sense, the air that comes into the carburetor, they neck it down, which then obviously produces low pressure. Let that settle in for a second. This restriction produces low pressure. It's probably the opposite of what you would actually think. And so, but in fact it does. And so if I illustrate that low pressure principle, so the way that I'm going to illustrate this is that what you have at least experienced is like if you took your garden hose out in your front yard and you put your finger over half of it, you realize that the velocity of the water coming out of the hose increases, right? And so the velocity does increase. That is hydraulics, it's not pneumatics with air, but that principle holds true in this example, that if I speed up the air between these two papers, all right, will the papers blow apart or will they come together if I blow through the middle of them? All right, so most people anticipate that they're going to blow apart, and so I'm going to go ahead and blow through these so that you can watch what happens. So if I hold them a little better like this, you can see they kind of curl. And if you think this is some sort of a party trick, then go ahead and reproduce that experiment at your house. So hopefully you're able to see that they actually come together. And so when I speed up the air through the middle by blowing through them, it creates low pressure, and then the air pressure on the outside collapses the papers in towards the middle. And so what ends up happening when they design the carburetor this way is as they restrict the air here, this is referred to as a venturi, then the velocity of the air increases, which creates a low pressure area in that venturi. Well, then the bowl in the carburetor that has fuel in it, the inlet of fuel into this is just a straw that's called a main metering jet, and it's orificed and calibrated to the bore of this carburetor. But when we have low pressure here and high pressure outside the motor, atmospheric pressure, then it works like a squirt gun and it pushes that fuel out into the airstream. And so there's more complexity to these circuits and these carburetors to be able to produce the desired air-fuel ratio given the physical operating conditions and some of the physics of what happens when you open a throttle plate and air pressure starts to balance out. But they have successfully produced a mechanical device that can deliver a running air-fuel mixture under a variety of operating conditions. When the engine is cold versus when it's hot, when you accelerate, when you're at cruising speed, when you're decel, all of these things, they've produced a mechanical device called a carburetor that can deliver a running air-fuel mixture. Does it do it as good as fuel injection? No. But did it get the job done? Yes. So carburetors are impressive. To be able to deliver the proper air-fuel mixture under a variety of operating conditions, a pretty impressive feat, and they're pretty heavily mechanical. But this was a non-computerized system. So gasoline injection gets categorized in a variety of different ways. There's different types of gasoline injection systems, fuel injection systems, and then what the direct injection systems that was common a diesel form of injection is also being utilized in gasoline vehicles nowadays. And so if we were going to break down these different fuel systems, we would categorize our injection systems as indirect injection and direct injection. Indirect injection sprays the fuel indirectly into the combustion chamber. So it's out in the intake manifold or in the cylinder head behind the intake valve, and it indirectly sprays fuel or introduces fuel into the combustion chamber. Where direct injection directly meters that air-fuel mixture in the combustion chamber directly. And so that obviously is an efficiency thing. That it is more accurate to formulate the air-fuel mixture in the ultimate in place of the combustion chamber than it would be to indirectly spray it in the air intake passage and hope that it all makes it in there, right? I can more precisely formulate an air-fuel mixture for the amount of air that actually got in the combustion chamber by doing it this way than that way. So you can see why this would be an advantage and even an efficiency, from an efficiency standpoint, to get better fuel economy and have more precise control. So of our indirect injection systems, we have two other categories that we would call throttle body injection, which we've already mentioned. That throttle body injection is what replaced carburetors, kind of bolted down in the place of a carburetor, and basically would flood the intake manifold with a homogeneous air-fuel mixture. So what we're referring to there is just the idea that you've heard of homogenized milk, where the milk and the cream are completely thoroughly mixed together. Where they're trying to thoroughly mix the air-fuel mixture, fuel and air, and it's being done from above the throttle plate, and so we flood the whole intake manifold with an air-fuel mixture, versus port injection that draws in air, and then at the point of the injector we formulate the air-fuel mixture. And so that would be referred to as port injection, where the injector is at the port, throttle body, the injector is at the throttle plate or throttle body there. And so with port injection, we have one injector per cylinder. The thing to kind of remember about TBI or throttle body injection is this was the move in the design that replaced carburetors. So it was the early move, unbolt the carburetor, bolt the TBI down in its place. And then to more precisely control the distribution of fuel, then port injection came along. When you consider throttle body injection, or even carburetors for that matter, if my carburetor is here and I've got some cylinders over this way, or I'll do it maybe this way so it's a little more visual for you. But if my carburetor's here and I've got some cylinders further away over here and I've got some cylinders further away over there, then the ones that are closest to the fuel source will get more fuel than the ones that are further away, right? So with port injection, they solve that problem. And they get identical fuel distribution because we've got 6 individual injectors for all 6 cylinders on this car. So we can distribute the same amount of fuel to every single cylinder. All right, and so that was a huge advantage to port injection over throttle body or carbureted for that matter. So with electronic fuel injection, this is now computerized fuel injection. There's a few different factors and subsystems that are involved. We've got our fuel delivery system, air induction, sensors, and then we've got our computer controlled system. So fuel, air, sensor, and computer controls. So when we look at these different systems here, when we're talking about fuel injection, what the computer is always trying to determine is how much air came in the system or came into this engine and how much the air weighs. All right? So that's really, because our air-fuel ratio is by weight, then it needs to know the volume of air that came in and then ultimately the density, right? Cold air is going to be heavier than warm air, right? A larger mass of air weighs more than a shorter mass, right? And so that's really what all these other sensors are all about, is trying to gather enough data to be able to determine how much air came in the motor and how much it weighs. And when we're talking about a computer control system, that there's a few different strategies for how they do that. But that idea for determining how much air came in and how much it weighs is referred to as air mass. So the computer is always trying to determine how much air mass came in, how much air came in, and then how much it weighs. And so our air induction system, we have the routing of the air, intake designs, air filtering to make sure the air is clean that comes into the engine. We have our fuel system that is responsible for supplying fuel up to the engine and then metering it at the injectors. The computer is taking information from a variety of sensors, making decisions based on what it's been programmed to do so that it can control these injectors. And so when we're looking at these sensors that are reporting to our computer, we have an airflow sensor or a mass airflow sensor that looks like this, that this is a mass airflow sensor that's on this throttle body here. And so this mass airflow sensor is just a little hot wire sensor that the more the air that flows across, there's a couple little wires inside here, that the more air that flows across those, the more it cools the wires off. The cooler the wires get, the computer knows more air came in. And so it's a pretty simple system that way. And so this sensor reports directly about how much volume of air came in. Then that will help in our air mass calculation. The MAP sensor is used in a couple different ways. A manifold absolute pressure sensor monitors engine vacuum, and as well as atmospheric pressure. When you first turn the key on, it will take an atmospheric pressure reading. If you guys will understand this, we say as we climb in altitude that the air gets thinner, right? That concept that as we climb in altitude, the air gets thinner. You guys have felt your ears popping as you drive into the mountains, right? As the pressure inside your own head tries to normalize with the decrease in pressure as you climb in altitude. And so as we increase in altitude, the weight of the air in our atmosphere is all weighing down on all of the air underneath it, right? And so at sea level, you have all of the weight of the air above it into the atmosphere pressing down, right? And as we climb up in altitude, there's less air above us and more air below us, right? So the pressure then decreases. As the pressure decreases, then the molecules of the air molecules can spread out further and further, right? The more pressure they're under, the more it compresses them down tightly, and to where they're more condensed, so that in a given volume of air, a foot by foot by foot, a given volume of air at sea level, foot by cubic foot, I should say, weighs more at sea level than it does at 10,000 feet. All right? So a MAP sensor not only takes a pressure reading of the environment, a baro reading we would call that, but it also has a relationship to the pressure inside the intake manifold, right? Because the pressure inside the intake manifold, lower pressure lets the molecules expand more, and higher pressure compresses them, right? So that air will weigh more in a given volume. And so MAP sensor and manifold vacuum also changes with throttle movement, right? And so if the throttle is closed and I have very low pressure inside the manifold, right, then that air would weigh differently than when the throttle is open and now I have atmospheric pressure or higher pressure, right? And it's also a relationship to what the driver is doing with the throttle plate. So we also have a throttle position sensor, which will also be an input to the computer for it to know how much air came in, because when the throttle plate's closed, not as much air will come in as when the throttle plate is open. Then we've got intake air temperature. Taking an air temperature reading, right, will help us determine density, right? Hot air weighs less than cold air. Coolant temp. We've established already and talked about the fact that when an engine is cold, then the fuel would want to condensate and stick to all the cold metal parts. And so this would be a factor the computer would want to know about, because when the engine's cold, it's going to have to add more fuel versus when the engine is hot and at operating temperature. And a cold start will have to compensate for that by adding more fuel versus when that engine's warmed up. So not just cold day, warm day, but also cold engine, warm engine. So then RPM, the higher the RPM, the more air that those pistons will move. So that becomes a factor as well. Then we get back to something called an oxygen sensor. So An oxygen sensor is different than a lot of the rest of these other sensors because an oxygen sensor is located in the exhaust and it does exactly what you would think it would do. It measures the amount of oxygen coming out of the exhaust. Now, it's not an incredibly intelligent device, although it is sophisticated, all right? So, an oxygen sensor, what it does is it reports back to the computer whether there is oxygen or whether there isn't. This is basically how it works. For this oxygen sensor, and in terms of our air-fuel ratio, if we nailed it and that computer precisely and accurately grabbed the exactly correct amount of air that came in and how much it weighed, and then it sprayed the perfect amount of fuel through these injectors to combine with the amount of air that came in, then when we burn that air-fuel mixture, then the oxygen combines with the carbon, and the oxygen combines with the hydrogen, and we get CO2 and water, right? So then no oxygen would be present out the tailpipe. If it misses the mark a little bit, and it doesn't add enough fuel, then there would be oxygen present out the tailpipe. So what ends up happening there is that if that oxygen sensor reports back to the computer, hey, I see oxygen in the tailpipe, then that computer will go, okay, well then I'll just spray a little bit more fuel. So it sprays a little bit more fuel. Then if that oxygen sensor says, hey, there's still oxygen in the tailpipe, it will spray a little bit more until the oxygen sensor says, hey, I don't see oxygen anymore. And then here comes a little bit of a problem. It's possible that the reason why that oxygen sensor doesn't see oxygen anymore is because now the computer has overfueled the car and then used up all the oxygen. And so the computer cannot tell the difference between if it nailed it at stoichiometric perfectly or if it overfueled the car. And so in that case, the computer has no choice but to back off and spray a little less fuel. And so what will happen when we're in fuel control is the oxygen sensor says, hey, I still see oxygen, so the computer sprays a little more fuel. Then the oxygen sensor says, oh, hey, I don't see any oxygen anymore, so the computer takes some fuel away. Sprays a little more fuel, takes a little fuel away. Sprays a little more fuel, takes a little fuel away. So it runs a little bit rich, a little bit lean, a little bit rich, a little bit lean, to where then on average, it's stoichiometric. All right? And that's the way that the system is intended to operate. And so that is your little update for computer controls. We have acronyms for all of these, which we'll kind of cover a little bit later on. So if we take a look at our fuel injection system components, we're gathering all of this information from sensors so that computer can make proper decisions about how to control the injectors and how much fuel to spray into the motor. And so a modern fuel system would be composed of our fuel tank that stores the fuel. We'll have typically an electric fuel pump that will push fuel up through a filter to the fuel injectors up in a fuel rail. The injectors are responsible for metering and delivering the proper amount of fuel into each cylinder, and then whatever fuel is not used gets returned back to this tank. So if we had to divide our fuel system into a couple different groups, these are the way that we would categorize the components in this fuel system. So we would have a fuel supply system that supplies the fuel up to the delivery system. The delivery system is going to meter and distribute that fuel in the proper amount to each one of the cylinders based on the operating condition of that vehicle, whether we're idling or accelerating or decelerating and so forth, cold start and whatnot. So the supply system components would include the fuel pump, filter, the tank lines, and then a fuel pressure regulator that controls the fuel pressure in the system. The delivery system components would be the injectors and the fuel rail, and then that's where we get into our computer controls that control these output components. So our old school stuff was mechanical fuel pumps. This is our mechanical fuel pump that would run off of an eccentric on the cam. That an eccentric is just like an egg-shaped globe that as that would rotate, it would depress this mechanical fuel pump and then cause this diaphragm to move up and down and pump and build fuel. They didn't build a lot of fuel pressure in these 3 to 5 psi, but this was a completely mechanical system. One of the things that I'll just share with you, because people don't talk about these older systems very much anymore, but I would assume some of you are at least hot rodders in here that would work on an older car. But these old mechanical fuel pumps had a rubber diaphragm in them, and they had weep holes just like a water pump has a weep hole. That if you ever get fuel leaking outside of this externally, then the diaphragm has gone bad. And then what ends up happening is that fuel from the bottom side where the lines would connect is coming up on the diaphragm side, where now it can leak out and into the crankcase. And so what happens on a lot of those in that case is that the oil level comes up in the crankcase. And so you get customers that have older cars, they won't know what's going on. Then if they check their oil, they'll check their oil like, oh man, it's overfull on oil, right? I drained some out the other day, and now I checked it a few days later and it's overfull again. I have no idea what's going on. And so we charge them to tell them. So if you ever are in that situation, then you would know what's going on those systems there. But mechanical fuel pumps like that, as long as that crankshaft and camshaft are turning, that pump's going to make pressure. All right. So electric fuel pumps are typically located back in the tank, and they push fuel forward from the tank. So they pressurize the fuel forward from the tank. Electric fuel pumps range in pressure. Some of your older ones were 30 psi or so, but some of the more modern stuff is making 100 psi. And so, but they're typically located in the tank. They don't have to be. Some of them are outside the tank, and they have a shorter section. They suck fuel out of the tank and then pressurize it. But a lot of them nowadays are located down in the tank. So throttle body injection often had electric fuel pumps as well, and they would push fuel under relatively low pressure at 9 to 15. Your port injection system's a lot higher. Some of your more modern systems will produce it over 100 psi. But what we had is in red is the feed line coming in, and then green is a return back to the tank. These are kind of older, cruder systems that pump would just run all the time, and it always made as much pressure as it could, and then they mechanically regulated it with a fuel pressure regulator. A lot of your newer ones, what they will do is if the pump has a max ability to produce 100 psi, then just like we talked about with our charging system, they would pulse width modulate or command it at 50%. And if it could make 100 psi, if it had power and ground all the time, then at 50% on, it would make 50 psi. If they wanted 75 psi, they commanded 75% on. And so that's what a lot of your newer systems do, is they know they don't need a lot of fuel volume when the throttle plate is closed because only a little bit of air is coming in. But then as they open the throttle plate and more air comes in, they command the pressure higher and higher from the fuel system. So they have the fuel supply system create the proper amount of fuel volume for the amount of fuel that's going to be used for that driving condition. Filters. Filters is the big maintenance side for our fuel injection systems. So this is a fuel filter here. So this fuel filter, there's service intervals for these fuel filters. And if they plug up and you try to make an electric fuel pump like this, push fuel through a plug filter, then it just burns up the pump. And so if you went home today, or you're already at home, but if you went over and turned your fan on in your house and you just held on to the fan blade, you turned it on, you didn't let the fan turn, you held on to it, you would burn up the motor in that fan, right? Making a fuel pump push fuel through a plug filter will burn up the fuel pump. Now, to put it in perspective, filters are cheap. $10, $20, right? Some of these fuel pumps are $1,300 in a BMW, right? This one's about $200. Some of them were, $450 when these first came out. But fuel pumps are not cheap, and fuel filters freaking are. So you make sure that you change your filters when you're supposed to. Now, not all of your newer cars have filters that are serviceable. Some of them have quote-unquote lifetime filters, but basically what that means is it doesn't have a serviceable filter. When the filter plugs up, it'll burn your fuel pump up, and when you buy a fuel pump, you can buy a filter too. So some of them are set up like that they supposedly have lifetime filters. However, it's worth checking into on your cars, your customers' cars, to do your customers right. If they have serviceable fuel filters, you should be changing them according to manufacturer specs. Just to clue in, because there's a lot of like Ford people, Chevy people, Dodge people, all right, in particular, a lot of those have serviceable filters, especially on your Chevy pickups. Your Chevy pickups have the worst fuel pumps of any manufacturer. They have the crappiest ones. They go out the most. I have a Chevy pickup, and I've had it for about 100,000 miles, the one that I have, and I've had to put a pump in mine, all right, within 100,000 miles. So I put 2 pumps in it. I take it back. I've had to put 2 pumps in 100,000 miles. So it is what it is, all right? They have crappy fuel pumps. You can do yourself a favor and change your fuel filters about every 15,000 miles, which is once a year for most drivers if you have a Chevrolet product. And so they already have weak fuel pumps. They don't need any help going bad. Changing your filters is one of the things that will help prolong the life of the pump, because guaranteed, you plug a filter, it'll burn up the pump. That is the #1 cause of fuel pump failures, is plugged up filters. So when I have a failed fuel pump on any car, one of the things I'm always going to check is to see if the filter is plugged up. Because if the filter's plugged up and you don't change it and all you do is fix the failure, you never fix the cause of the failure. And so you'll just, the same reason that burned up the last pump will burn up the new one. Attached to most of your pumps will be a sending unit. So when you have a fuel injected vehicle, the sending unit will typically be attached to the pump and the tank. Well, on carbureted vehicles, this was a separate component that was back in the tank because the fuel pump was mechanical and up on the engine block. So on your fuel injected vehicles that have pumps in the tank, the sending unit is typically attached to the pump in the tank. And so this is a very simple device that this changes resistance based on the position of this arm. And so when you have a full tank of fuel, then the resistance value is different than when you have an empty tank of fuel. This is calibrated to a gauge in the dash. And so these, in a really simple sense, this is the way that it works. That with this view, these gauge and the sending unit go together. And so you can see when the tank is empty, we have all of this resistance. So the resistance is high to get back to ground for the sender, so then that would read empty. Then as we fill up the tank, there's less resistance here to get to ground, and so then that would then proportionally change what's displayed in the gauge. So that's your sending units there. A lot of times the sending units go bad because they have mechanically touching wearing parts, and so you'll wear a bad spot where you ride around with fuel the most, which for most people is towards empty. Spend a lot less time with the tank full of fuel. Like I've seen people at the gas station, and maybe you're one of them, that goes in like, I'd like to put $5 on pump number 2. So that's that. So if they're riding around quarter a tank to empty most of their life on that car, then that's what's going to wear out first. The float in here, some of them were brass or little plastic floats that could kind of wear through and fill up with fuel and then sink. A lot of your newer ones are kind of composite like this, where they're just kind of like a foam filter, to where they usually don't have that problem anymore. So with our fuel delivery system, this is where we're metering the fuel that makes it to our cylinder. The fuel pressure regulator was still something that's part of our supply side. And so the fuel pressure regulator is what the pump pumps against. So there's the fuel pressure regulator on here. This is a vacuum operated one. The line that comes from the pump is over here, and it'll pressurize this whole rail and pump against the outlet of this fuel pressure regulator. Now, the more fuel it lets return, the more it bleeds off and lowers the fuel pressure down in this rail. The more it restricts, the higher the fuel pressure will become. And so this fuel pressure regulator, some of them are mechanical, but a lot of them are going to be vacuum operated on your port systems. And then others, they just vary the speed of the pump. The faster they spin the pump, the more volume and pressure it produces. The lower they spin the pump, the less volume and pressure it produces. But this is the way that these fuel pressure regulators will work, is that they'll have a vacuum line that comes off of that fuel pressure regulator that looks like this. So this would plug in here to the intake manifold. And so that's acting on a little rubber diaphragm inside that fuel pressure regulator. So when the throttle plate is closed and manifold vacuum is high, then that vacuum acting on that diaphragm will pull and unseat that little diaphragm and let a lot of fuel return back to the tank while we don't need a lot of fuel volume. Then when engine load is high because we've opened the throttle plate up and we would need more fuel volume, then that spring that's in here will push on this diaphragm and seat it off and seal it off to where no fuel returns back to the tank. Then all of the fuel that fuel pump produces would get utilized by the injectors and burned in the motor. So a fuel injector is an electromechanical device. So it has an electronic portion and a mechanical portion. I'm going to grab a little demo over here. This is my Halloween ray gun. No, it's an injector. So the way that this works, anytime we have a winding of wire that we energize with electricity, it produces a magnetic field, and we're using a magnet that when we energize this, then this would be magnetic. And so when we build the magnetic field up here, then this pintle being magnetic would pull up, and as it pulls up, then it would let fuel spray out the tip. When they de-energize that magnetic field and release the power and ground and the magnetic field goes away, then the spring that's in there would push the pintle back down and seal off that injector so that no more fuel sprays. So that's the way that this works. They use electricity to build the magnetic field in the coil windings and injector. It lifts up the pintle, fuel sprays, fuel's coming in through a fuel inlet and is just waiting there. It's got a little basket filter. The electrical connector would be here on this injector. And so when they energize the windings in there, builds a magnetic field, pulls the pintle up with magnetism. When they release the power and ground of this injector, then the magnetic field goes away and then a spring reseats that injector and no more fuel sprays. So that's the way that those injectors are designed to work. So our air induction system here, we've got our filter that traps all our debris and dust. Don't get lazy about changing those, right? Filters are cheap, motors are not. You've got a throttle valve that controls how much air comes in through our throttle body and throttle plate. And then we've got sensors that are tracking throttle position as well as trying to feed that computer information so it can determine air mass. And we've got ducting that directs that air to our intake valve or back, our inlet into our combustion chamber. So this is our just a cutaway view of an engine that ultimately we're trying to get an air-fuel mixture here. Throttle plate is up here that controls the airflow. So the airflow that comes in, we actually do want some turbulence. The little lines that are in there are really showing that the bends and the curves in these intake manifolds actually help create turbulence like a blender so that when the fuel is introduced by the injector, it kind of swirls and mixes well. Because we don't want just pockets of fuel and then pockets of air, because if I've got some air and fuel mixed here and then it hits a solid pocket of air, the flame goes out, right? So I need air and fuel thoroughly mixed. Part of the strategy for that is creating these turbulence in these bends. Now obviously, a bend like this, making a sharp bend doesn't help this motor breathe very well, does it? This is not a performance strategy. This is a fuel efficiency strategy. If you were really trying to make max performance, this would be a what? A straight shot intake manifold. But these cars are production cars. We're trying to get good fuel economy. There are some manufacturers, and Ford, this is one, like, hats off to Ford. They were one of the first ones that I'm aware of to come out with dual plane manifolds, to where they had a fuel economy manifold like this, and they had a performance manifold all built into the same one, that they could switch passage and shut the door off here and open a different one here and have like a straight shot performance intake and a fuel economy intake all on the same engine. So pretty impressive. So one of the other things about this diagram that I would point out to you as well is that while the throttle plate is closed, then in this case the throttle plate is closed and manifold vacuum is low, so we have low pressure inside the motor, high pressure outside. When the throttle plate is open, then we have high pressure in the intake manifold, because atmospheric pressure is high pressure. So throttle plate closed, low pressure but high manifold vacuum, we call that. Throttle plate open, we have low manifold vacuum, high pressure. So this is our throttle valve, or the accelerator pedal controls the throttle plate. Those of you that hopefully are going to be taking Mr. Posey's class in the first 8 weeks, the B20 class in the fall, I love how he describes this. He does not call this a gas pedal, he calls it a air pedal. And he's exactly right. This is not a gas pedal, right? Because when you step on it, it doesn't let gas in, it lets what? Air in. So this is what controls the amount of air that comes in. This is one of the things that makes a gasoline engine less efficient, is that to control the RPM, we choke these motors out and control how much air we let them have, right? The more air we let it have, the more power it makes, right? So when we try to throttle them down and control the RPM, we choke out the air. Well, this is a restriction, right? So right away, that hurts the fuel economy of these vehicles. So this is just another depiction of what we were describing before, that when the throttle plate is closed, we have high manifold vacuum, but we have low pressure. And when it's wide open, then atmospheric pressure tends to balance out inside the intake manifold, so then we have low manifold vacuum and high pressure. Because keep in mind, the pistons are moving in the cylinder, what generate the low pressure. Well, they're pulling against the dividing line of this throttle plate. That everything below the throttle plate is manifold vacuum from the intake strokes of these pistons, and everything above the throttle plate would be atmospheric pressure. Well, then if I make the dividing line not a dividing line, I have the car wide open throttle, then the pressure is the same inside the motor and outside the motor. So we get to electronic throttle controls. So I've introduced this idea at least a little bit in the past with the relearn procedures and when your battery goes dead and stuff like that. But I want to introduce this concept. It's one of the ways that we are getting better fuel economy now than what we used to, because the computer can control the throttle to get you better fuel economy than you can. All right? So this in reality now, you have no direct control over what happens to the throttle anymore. You don't get to control it. When you step on this accelerator pedal position sensor, that's what APP is, then you are asking this computer, I would like to accelerate my vehicle, right? It's like, okay, I see that you want to do that. Okay, I'll open the throttle plate for you, right? And so he opens the throttle plate, and the throttle position sensor reports back like, hey, okay, I opened the throttle plate. That's how this works nowadays with electronic throttle controls. The really cute thing that I think is hilarious is that when these systems came out, you had manufacturers that would fake you out with the performance that their car had. So, and they do it still. That like you would have a pretty no power motor, like a Dodge Neon or something like that. And so the driver of the car barely steps on the accelerator pedal, right? And so maybe they step on it 10%. But this computer has been programmed that if they barely step on the pedal, we're going to open this guy 30%, right? So when they open it 30%, this car like takes off, right? And the perception of the person driving is like, oh dang, this thing's got a lot of power, right? When in reality, the amount that the computer opened the throttle plate was not proportional to how much you stepped on the pedal, right? And so it gives the perception to the driver that this car has more power than what it actually has. Because the driver's like, man, I barely stepped on the pedal and this thing almost did a burnout, right? So when in reality, they showed you a third of the power that vehicle had, right? You barely stepped on the pedal, it went a third of the throttle opening. So manufacturers have had a good time in kind of selling, misrepresenting in a sense, the performance that their cars actually have when they move to electronic throttle controls, and kudos to them, right? My dad, he bought a new truck, and he had always driven cable-operated vehicles to where when he bought a new truck, it was drive-by-wire like this or electronic throttle controls, and he freaking did burnouts for like the first 3-4 months that he had that truck, like because he wasn't used to the responsiveness out of this. And so the responsiveness out of electronic throttle controls is superior to the cable-operated stuff, because when you consider these older ones like this, because I had control over the throttle, I could open the throttle, and then the computer had to catch up with me, right? I opened the throttle, air came in, and then the sensor's like, oh, hey, they opened the throttle, right? Where with electronic throttle controls, they're on the front end of this, right? You step on the pedal, it opens the throttle, and as it does so, it's getting the right air-fuel mixture the whole way, right? Where with this system, I could kind of surprise the computer, like, if I went from here to like wide open, then I have air rushing in and the computer's trying to catch up with what I'm doing, right? Where with this system, it's on the front end, right? When you step on the pedal, it's opening the throttle, supplying the right amount of air simultaneous. So it knows everything that's going on in this case. So these tend to be more responsive than your cable operated systems. So wrapping it up, we're getting to our computer controls here. The primary computer on this would be called an engine control module or a powertrain control module. An engine control module is a computer that just deals with the components necessary to control the engine. A powertrain control module, or PCM, includes engine and transmission as part of the powertrain. And so based on the inputs that come from the sensors, then that computer is going to make commands to change the fuel delivery and try to deliver the proper amount of fuel based on the air mass that came in. So it's making those decisions based on what it's been programmed to do. It's looking in lookup tables like we looked at with ignition systems. There's a whole map for fuel control as well. And then it's going to monitor the system for proper operation, all the variety of sensors that are reporting to it, all of the outputs that it's controlling. It's monitoring those for proper operation. And if they don't operate properly, or if they're malfunctioning and the computer detects it, then it turns the check engine light on the car. And so the sensors we basically looked at, a variety of these different sensors, from RPM from our pickup, our TPS, coolant temp, oxygen sensor, mass airflow sensors, even the AC compressor is a load on the motor that the computer has to account for, or things like power steering, the charging system we've talked about. A knock sensor I haven't brought up, but if detonation is detected, then that sensor reports to the computer and it would respond by retarding the ignition timing, but those are inputs there. Baro, we've talked about atmospheric pressure. Then it's controlling these outputs: spark timing, the fuel pump, fuel injectors, idle of this motor, other emissions devices like an EGR and air pumps and so forth. And so these, I at least want to expose you to the acronyms that we use in the automotive industry. We use tons of those, but as it relates to our conversation about trying to determine air mass and the sensors that are coming and feeding this computer information so it can determine how much air came in and how much it weighs, there's these sensors involved that are primary sensors. The throttle position sensor, we usually don't waste that much breath. We would call it a TPS. Mass airflow sensor, we would call a MAP. Manifold absolute pressure sensor is a MAP. The engine coolant temp sensor is an ECT. Intake air temp, IAT. Crankshaft position sensor is CKP. Camshaft position sensor, CMP. And oxygen sensor we would refer to as O2. So as you go through the auto program and take different classes, there's going to be a variety of exposure to a lot of these acronyms and a lot of other terminology, and this is enough to get you started to where we can have deeper conversations about fuel systems in the future.